Okay, in this section, we're looking at velocity time graphs. In a previous unit, I did position time graphs, so look back at that, and that way this is kind of the complete lesson to compare the two. And when we are done, you will be able to answer a question like this, showing what type of motion does the picture show with a graph and something like this. So a velocity time graph, first of all, you know it's a velocity time graph because it's velocity on the y-axis and it has time on the x-axis. And then the kind of motion that's going on in there is represented by the unit meters per second. So this would be 0 meters per second. Up here you're going 25 meters per second. Here you're still going 25 meters per second. And then you go past the 0 meters per second point or rest. And at the end you're probably going about, looks like around 15 meters per second, but backwards or negative. Okay, so in general, last questions ask you what the slope of a velocity time graph or position time graph is. And on a velocity time graph, it's nothing more than velocity over time. And just a reminder, that is acceleration. So the slope on the velocity time graph is acceleration. And now what is constant forward motion going to look like? Remember, this is a 0 point. This is where you're at rest. Anything below that, you're going backwards. Anything above that, you're going forwards. So this is important to note. So anything here, forward, here, backwards. And it's only one stop, right here where you're at rest. Okay, so this is anything above this line. It could be this arrow, 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 it could be this arrow. Once again, a little overkill. But anything above that line can be constant forward motion as long as it's a flat line. You want to have, if this is 5 meters per second, it needs to stay 5 meters per second for it to be constant velocity. This also means that there's zero acceleration. Constant backward motion, you're going to do kind of the same thing, but you're going to be below that line. So anything down here, once again, it has to be a flat, straight line. Here in this line right here, you're going -4 meters per second, and you continue to go -4 meters per second at the end. So you were going back 4 meters every second backwards, every second you were going. Constant acceleration on a velocity time graph is going to look something like this. In this picture, you went from, let's say, 0 meters per second, and maybe at the end you're going 20 meters per second. Once again, there's no numbers in here, so I'm just making things up. But you're going there at a constant rate. So you're speeding up 0 meters covered per second to 20. You're now covering 20 meters every second, and at a constant rate because the slope is equal the whole time through. Constant deceleration. Well, that's going to be a backward motion. So constant deceleration, depending on where you find it, would look different. When the velocity is positive and the acceleration is negative, you have a deceleration. But something would be different on this side. If the velocity was negative, the acceleration would have to be positive. That actually is considered deceleration too, because you were going a negative, let's say, let me put in a number, 10 meters per second squared, and you went from going backwards 10 meters per second squared all the way to the point where you would be at 0 meters per second. Actually, that should be just meters per second, not seconds squared. It's the velocity. So you went down to rest, and if you kept on going, you all of a sudden switch it up. Okay, so the only place you're sitting still or not moving is going to be right on that line, the 0 meters per second line. And so let's look at an example question. Determine the velocity traveled at 16 seconds. Okay, at 16 seconds, what is the velocity you're traveling at? Let's change this, traveling at 16 seconds. If it's a velocity that you're traveling at, for example, right here, this is a velocity time graph. You can just go ahead and you can just pick off the numbers. If it's asking you for velocity, which this question was, sorry, I changed it earlier and it didn't make sense, but here I'm asking you what the velocity is. If you ever ask for the velocity, it's going to be exactly what you read off the graph. At B, you were going 50 meters per second. Okay, now on a velocity time graph, you can only get givens if you're asked for something else. Distance and displacement, most of the time you can call it x and just do the common math here. We're going to do that. So the distance traveled is x. In the BC interval, Well, you know what? This is a constant velocity. You're going 50 meters per second, and you're staying at 50 meters per second. So instead of using VIs and VFs, we're going to go ahead and say V is 50 meters per second. So V equals 50 meters per second. And now we also need a time. So B goes from here to B to C is 16 to 30, or 30 minus 16, which will end up being 14 minutes. So time equals 14 minutes. And now we have V equals X over T, just a common equation we've done before. X equals V times T. And when we plug in the numbers, V is 50, time is 14. So we're going to get 700. And that's going to be meters. And there's our answer for this one. Okay, another question where you have a distance traveled, but here we're looking at the AB interval. Now what you're going to notice here is you start off with an initial velocity of 0. It's not constant velocity. And you ended off here at a velocity of 50 meters per second. And the time it took for this one to occur was 16 seconds. So here's your time, 16 seconds. And so now we can go ahead and solve for x equals question mark. When I started off at 0, I got to a final velocity of 50 meters per second, and I did this for a time of 16 seconds. And there's an equation that you can use. X equals VI plus VF over 2. So here you have acceleration going on, but this is like saying, okay, I accelerated the whole time, but instead of taking that overall, I'm going to go ahead and say, let's go ahead and pretend like we're just cutting it in half. And we're going to pretend like that happened the whole time instead of what actually really did occur. And this is how you get this is more of an average velocity equation. Then we have a time of 16, or there's your, and then it's going to be multiplied by time. Plug in our numbers, we get xi 0 plus 50 over 2 times the time, and time here is 16. So it's going to be 400 meters. There's your answer here. Okay, acceleration. Okay, once again, it's not something we have on here, but we have all that we need. There's a lot of givens here. Here we start off with initial velocity of 50 in the C to D interval, and we got to a final velocity of 0. And the time it took was 10 seconds. So A equals question mark, VI equals 50 meters per second, VF equals 0 meters per second, and we have a time of 10 seconds, and now we have everything we need. And there's one specific equation, A equals change in V over T. There's another one that's a little more complicated, but that is nothing more than V final minus V initial over time. And V final was 0, V initial was 50, and it should be a negative because we're going to decelerate, over 10, and this would be negative 5 meters per second squared here. So there's our answer, or 5 meters per second squared backwards if you want to be more correct than just having a negative. Okay, so let's look at an overall graph. You need to be able to see a graph and tell exactly what's happening. So the way I see it, in a way that makes it easier for students, is to go ahead and not say 0, but say 0 meters per second. You start at 0 meters per second. You weren't covering any meters per second. And you got to 10 meters per second. So what you did here is you accelerated. And you accelerated at a constant rate because the slope is the same. And then from there, you went ahead and you went a constant 10 meters per second. So at this instance, you're not accelerating. You have 0 acceleration. You kept on going the same speed. And from that point on, it looks like you went ahead and you started to decelerate. You went from 10 meters per second all the way down to 0 meters per second here. Sorry for my pen, it does some weird things. And then you stayed at rest. So this is one spot where you're at rest. You were at rest right here. You were at 0 meters per second every second. And then you started walking backwards. So during this interval, you went from 0 meters per second to negative 10 meters per second. So now you're traveling in a negative direction or a backwards direction. And you did that for 4 minutes. So if you're going to do a position time graph or trying to compare a position time graph to a velocity time graph, you really have to do a little more work to get it perfect. You can get a generic one, but if you want to get it perfect, you need to do some calculations. you have to figure out what's the displacement during this first interval. How about the second interval? How about the third interval? And everything and so on and so forth. So I did that, and you're using either this equation if there's acceleration going on, or using this equation if there's, and this comes from v equals x over t. You've seen this one earlier, but v equals x over t becomes this if there's constant motion. And when you do the math, you find that in the first interval, you go ahead and we're going to go ahead and start at the origin because the velocity time graph doesn't really tell you where you start. You can't use that to tell you where you start. So I'm just telling you you're going to start at the origin. And for the first 5 seconds, you travel all the way up to 25. Should be a constant velocity going on. You're covering, you have, so it's not constant velocity. This one is actually accelerated motion. So let's go ahead and change that up a little bit. So during this first interval, you get to 55, but you get to 55 because you are accelerating. And I can tell that because you went from 0 meters per second to 10 meters per second. So let me make sure I get this right for you. It's going to be a curve up like this. So you have a curve going up at this point. It looks like a straight line, but it's curved. And from there, at that point, you're going to have a constant velocity until the next 10 seconds. So the next interval is going to go from 5 to 10. And so for the next interval, you're going to have a constant velocity. And during that interval, so right now you're at 25, you're going to cover 15 more. So I did the math. You're going to cover 15 more meters. So right now, so if we're at 25, we're going to be at 75 when we're done with this. So this is going to be a straight line. Once again, this should be curved. Let me make it a little less ugly. Let's try this one more time. So it should be curved. So I'll go ahead and have it a little more obviously curved. And then you have a straight line because you have constant velocity. And then all of a sudden what happens here is you start to decelerate. You start to slow down. So you're still going forward the whole time. You're going forward until you get down to 0. You're going forward the whole time. But let's figure out, to make it exact, we will be at 100 by the end of this interval. So at 15 seconds, and I already kind of paced this out for how much we're going to go, we are going to go slower and slower and slower. So this again should be curved. But this one should be curved down. So it's a little harder to see. Let's try that again. And it would be curved down. Let's go ahead and have it curve a little bit down. Okay, so at this point in time, after 15 seconds, we have covered a total of 25, 50, 100 meters. And then we're at rest for 1 second. It's time for a break. And lastly, at the very end, we're now going to cover negative. We're going backwards. We're getting faster and faster going backwards. So it's going to be a curve, but it's going to be going away faster and faster from that 100 meter mark. And we do this until the very end. And when we're at the very end, we are going to be exactly at 20 meters less. So we're going to be our total displacement here from start to finish. From start to finish, our total displacement would have been 80 if that was meters. And our total distance covered would have been 100 plus we came back 20. So our total distance would have been 120 if that was the question here. So now after this, you should look at, if you're going to answer a question, and you should be able to answer this now if you looked at both videos, position time, this is the same as saying displacement time. So that's not x for x-axis, but y-axis, or but it's the y-axis in this case is the displacement, which is x, which x stands for the variable for displacement. So I'm going from 15 meters all the way down to 5 meters at a constant rate. So once again, plug in numbers, and so therefore you're going to go constantly backwards. This next question, now we're talking about velocity. We went from 10 meters per second to, let's say, 2 meters per second. We were slowing down the whole time, but at a constant rate. So we're going to go ahead and we'll call that deceleration or decelerated motion. Okay, what type of motion does this picture show? We went from 0 meters per second all the way up here to 10 meters per second. So we're getting faster and faster, covering more distance per second. We are going accelerating. We're accelerating ourselves. And then on a position time graph, that same acceleration is going to look like this. You went from 0 meters to 10 meters, but you didn't do it at a constant rate. That rate kept on increasing. The distance you were covering every second was increasing. This is also going to be accelerated motion. Once again, you have to look at the graph you were looking at and realize what graph you're looking at. What type of motion does this picture show? We have velocity and we have time. You went 5 meters per second, and the whole time you're going 5 meters per second. You never sped up or slowed down. This is going to be your constant acceleration, but what direction? We are on the positive side, so we're going to be going forward. This would be positive forward constant velocity. And there's a lot of different ways to describe it, but it's going to have something about going at the same speed the whole time, same velocity the whole time. In this case, velocity, because you can't have a negative speed. So constant forward acceleration, constant forward velocity. What type of motion does this picture show? Okay, so we went from 5 meters, once again a position time graph, to 15 meters. And we went there at a constant rate. So there's going to be, you are going forward at a constant, and once again, the slope of a position time graph, x over t, is velocity, so constant velocity. This picture right here, this is where you're at 10 meters and you're still at 10 meters. You never moved anywhere. You have no motion, or you're at rest. This picture here, you are at 0 meters per second. You don't cover any meters per second, and you still aren't covering any meters per second. Once again, you are at rest or no motion.